Okay, today we're going to talk about the equations of linear motion. You've got these in physical science, and specifically the cases where you have constant velocity or constant acceleration. So, how do we model distance over time with constant velocity? Well, d equals v naught t, where d is the distance traveled, v naught is the constant velocity, and t is time. It's pretty straightforward. If you're moving at a constant velocity, just multiply the velocity times the time to tell how far you've moved. So, for example, if you start running in a straight line at a speed of 7 meters per second, how far will you travel in 1 minute at that velocity? Well, d equals 7 meters per second times 60 seconds equals 420 meters. Straightforward. Now let's look at this as a little bit more complicated model, just slightly. If you start 2 miles due west of your house and you ride your bike west at 15 miles per hour for 45 minutes, how far will you be from your house? Our equation isn't quite good enough here because we can't account for that 2 miles, that starting position. So instead we use the equation d equals d naught plus v naught t, where d naught's the starting distance, the starting position. And using that, we can answer this question because now we know that d naught is 2, v naught is 15, and t is 45 over 60 because the velocity is in miles per hour and the time was in minutes. Well, 45 minutes is 45 60ths of an hour. So d is equal to 2 plus 15 times 45 60ths equals 13.25. So in other words, you'll be 13.25 miles west of your house after 45 minutes. This is a pretty straightforward equation that models a lot of really useful stuff. So now let's go for the more complicated case where we include acceleration, where we have constant acceleration. And this is typically like gravity or the acceleration of a rocket motor or some other situation like that where you have an approximately constant acceleration. So it's d equals d naught plus v naught t plus 1/2 at squared. D again is the distance traveled, which you can think of as position. D naught is the starting position, how far you are from your reference point or your origin. V naught is the initial velocity, t is time, and a is the acceleration. So let's say you drop a marble off a roof of a 100-foot tall building. Let's create a model for its distance above the ground at any time t. So d naught is 100 feet, v naught is 0, and a is negative 32 feet per second. The acceleration of gravity, which is approximately constant in this case. And it's negative because it's going down, but our distance is measured in distance above. So the acceleration is opposite the direction that we're measuring the distance from. So we have d equals 100 plus 0t plus 0.5 minus 32t squared. So d is going to be 100 minus 16t squared. It's a quadratic equation. We can work with that. So how far above the ground will the marble be after 2 seconds? Just plug in the 2 there. D equals 100 minus 16 times 2 squared. And we solve that to get 36 feet. So after 2 seconds, the marble is 36 feet above the ground. Now, the other situation we can model here is velocity, right? Maybe we want to know the velocity of that marble. Well, velocity over time with constant acceleration is just equal to the initial velocity plus the acceleration times time, right? If you're going 50 miles an hour in your car and you accelerate at 10 miles an hour per minute, for a minute, you'll be at 60 miles an hour. So v equals v naught plus at, where v naught is the initial velocity, a is the acceleration, and t is the time. So let's go back to that marble dropped off the building. What if we want to know how fast it's going when it is 36 feet above the ground after 2 seconds? Well, v naught equals 0 because it's dropped with no initial velocity, and the acceleration of gravity is 32 feet per second squared, or 32 feet per second per second. So we get v equals 0 plus negative 32 times 2, which is negative 64 feet per second. This should be a negative. But other than that, that's how we get the velocity. It's traveling 64 feet per second down at the end of that. So now